With this lecture, we are going to begin our study of gases. So one of the most important concepts behind understanding a gas's behavior is pressure. Pressure is defined as a force per unit area. You can imagine air molecules as balls bouncing off a surface. So if you throw a ball against a wall, the ball impacts the wall, pushes on it, and then bounces back to you. And the same thing happens with these air molecules. They're bouncing off of surfaces. And not just air molecules, but really any gas. So nitrogen and oxygen and carbon dioxide and argon of air, but then also other gas molecules in other samples. And so pressure is the force of these molecules hitting the surface divided by the area. So that means that concentration and pressure are directly proportional, because as you expand the surface, then the pressure is going to decrease because you have you've increased the size of the denominator. So I want to talk briefly about collision theory, and this will come up a little bit later in the chapter, but you may have also heard of kinetic molecular theory in other classes, and it's a way of thinking about how gases behave. And so what we're talking about is a way of explaining what we see. So using these ideas, we are saying that pressure is the result of molecular collisions, and that fewer particles means fewer collisions, which leads to lower pressure. So in this example of this jar, we have more air or more gas particles in this jar than we do in this jar. The area, the volume is the same, but since this container has fewer particles, there are fewer collisions between the walls of the container. Therefore, there's lower pressure. And this is one way of thinking about how the pressure of something comes from the collision of the gas molecules with the surface. So there are a number of units for measuring pressure, and we're going to talk about a few of these and do a couple of conversion calculations to keep up with our dimensional analysis skills. So let's take a look at what these mean. So there are a number of different units that you will see for pressure, and one of them is the Pascal, and that is a Newton per meter squared. So this is really saying that pressure is a force per unit area. Because we have a Newton per meter squared. That's what a Pascal is. And then PSI, or pounds per square inch. This is probably one that you're somewhat familiar with, at least because I think most American tires have PSI ratings. There is a unit called the torr. It's kind of a made-up unit that really means 1 millimeter of mercury. And we'll talk about millimeters of mercury in a little bit. And then in inches of mercury, how many inches of mercury are raised by the pressure. And finally, atmosphere. Atmosphere is a unit that is derived because it is the average air pressure at sea level, and we have defined it as 1 atmosphere. And so we will use these types of units. Generally, we'll use atmosphere and millimeters of mercury, or torr. Those tend to be the most popular. But it really just also kind of depends on your scale, right? So if you're looking at pascals, or if you're looking at atmospheres, or you're looking at torr, that'll change the scale that it's really useful. So let's do a couple of practice problems. So in this example, we have 30.44 inches of mercury, and we want to convert it to PSI. So we look here at our conversions, and we see that at the average pressure at sea level is 29.92 inches of mercury and 14.7 PSI. So those are equivalent measurements. So we can set up our conversion factor using 30.44 inches of mercury, and we can multiply that by 14.7 PSI per 29.92 inches of mercury. And now you'll see that our inches of mercury units cancel. So we multiply 30.44 by 14.7 and then divide by 29.92. And we get 14.96. So we could either leave it as 14.96 or we could round it to 15.0 PSI. So millimeters of mercury is a common unit that comes from the use of the mercury barometer. At sea level, a column of mercury will be about 760 millimeters or about 30 inches. And we use mercury because it's much more dense than something like water, for example. The instrument would be rather unwieldy if it was water. And so 1 millimeter of mercury is a torr. Okay. And so 760 millimeters of mercury would be 760 torr. And you'll sometimes see that as a unit. So inside this tube, it has been evacuated of all air, so there's no pressure pushing down on the mercury here. This is completely empty. So then the way that the mercury climbs the tube is the atmosphere molecules, the molecules of gas in the surrounding atmosphere press down on the pool of mercury and force it up this tube. And so we can measure the height of this column of mercury to determine the pressure. Another common device is something called a manometer, and this is a sample. This is like a way to look at pressures in a lab. It's not quite as useful as the mercury barometer for telling an exact pressure, because what the manometer tells you is it tells you relative pressure. So you have a sample of a gas inside the bulb here, and then only one end of the tube is open to the atmosphere. And so this dense liquid is being hit by the atmospheric pressure. So the gas molecules in the atmosphere are pressing down on the sample of liquid in here, which is usually mercury. And then the high pressure gas or low pressure gas that's over on the other side is then pushing down on this side. And so there is a height difference in pressure from this side versus this side. And that pressure differential is what you can get from a manometer. So if the pressure of the gas sample is greater than atmospheric pressure, then the mercury level will be higher. So this is a high pressure gas. If this were lower, then this side would be higher. And this only ever measures pressure relative to atmosphere. It doesn't tell you what the atmosphere is. And so you would need to use the barometer for that. So I want to finish up our introduction to pressure by talking a little bit about blood pressure and how we measure it. So So when the arteries of your circulatory system constrict, the blood pressure increases. And as you have increased blood pressure, your heart has to supply more force to push the blood through the body out to the tissues that need the oxygenated blood. And so the reason why we always see our blood pressure reported in two numbers is because this is really two pressures. The numerator is the systolic pressure. And that is the pressure when you have the heart is at the peak pressure. And then when the heart is relaxed, that is the lowest pressure. So that would be our diastolic pressure. And so the way this works is restrict the blood flow. And then as the technician slightly releases the valve to somewhat release the pressure, as soon as they can hear the pulse, they know that that is the systolic pressure. And then when they lose the pulse, that is the diastolic pressure. So that's how that is actually measured. And so what we usually have, this is the higher pressure. So this is our upper limit here. And then this would be the lower pressure. And you always, generally, the American Heart Association recommends for a healthy adult, the blood pressure is 120/80 or lower. Now, oftentimes, you'll see slight increases in one of these numbers, and that'll be termed elevated blood pressure or risk factor for elevated blood pressure. And usually simple lifestyle changes can fix those problems. But if you have long-term sustained high blood pressure, far above 120/80, the problem with that is your heart ends up working so much harder to constantly be pushing against the increased, the constricted arteries. And so that can lead to heart damage, heart disease, things like that. And so understanding how pressure works, that it is a force against a surface, can make things like blood pressure make more sense to us.